In this video, I'm going to focus on the turbulent channel flow case. I will show you how to generate the statistics for Reynolds star 180, which is a well-known test case, and I will also show you how to use ParaView for the snapshots. The statistics will be generated with our post-processing tools called Py4 Xcompact3d, which is a Python-based framework, still under development, but it is now ready to use to generate the statistics for the channel flow. But of course, feel free to use your own post-processing framework to generate the statistics. So the first thing I'm going to do is I have a channel directory, and I'm just going to git clone the Py4 Xcompact3d framework. So very easy. And the only thing you need to do is pip install dot, and that will of course I forgot to go in the Py4 Xcompact3d directory, and that's it. The Py4 Xcompact3d framework is ready. So in my channel directory I have the Xcompact3d code, and I have the Py4 Xcompact3d. I'm going to go in the example directory channel flow case, and I'm going to load the DNS Reynolds 180 LR for low resolution explicit input file. Here I'm going to go through it very quickly to explain in more detail the most relevant parameters. So as I said, the resolution is very coarse. This is to run the simulation very quickly on a workstation. We are using a stretch mesh in the vertical direction, and this is controlled by a beta parameter, and I will show you that we are now providing a small tool to determine what beta should you use depending on the mesh resolution in the y direction and your Reynolds number. Computational domain 8 by 2 by 4, normalized by half of the height of the channel in the y direction, so 2h here. The Reynolds number is based on the center line velocity of a Poisson profile, so 4,200, and I will show you how we came up with this number. Because we are using periodic boundary condition in the streamwise direction, we need a forcing term. So here we are using a constant pressure gradient. We are running 100,000 iteration. An important parameters, if you go down here, is how do we generate a turbulent channel flow. We are starting from a Poisson profile with a random noise. We are adding a rotation to trigger turbulence, and we do that for 5,000 time steps. So this is also a parameter that you can control, but it means that very quickly after 5,000 time step we get turbulent channel flow, and we wait until 4,000 time step to get perfectly symmetric turbulent channel flow, and then we collect the statistics from 40,000 to 100,000. Okay, so these are some parameters that you can change, but for this video I'm going to use the default parameter. Other point I want to mention is that we are using a Range-Ikuta 3 time advancement scheme, and we are using the conventional implicit 6-order schemes for the first and for the second derivative. So there is no extra numerical dissipation. So as before, you can launch the simulation as you can see here, and I think I'm not going to do it now, but I think it will take just under 5 hours on 16 core on my workstation. Okay. So I have saved the snapshots. So this is in the data directory. In my case, I call them data channel. I'm just going to open ParaView, and then I will show you very quickly, just you can check that you have a fully turbulent channel flow. The most interesting part, I guess, for this video is to generate the statistics. So for ParaView, as before, you need to use the XDMF reader file. So I'm just going to look at the Q criterion for a value of 1. Here you are. I'm going to color it with UX, and you can run the simulation. So you have your channel flow here. another potential thing you might want to do is you might want to take a slice here. I'm going to remove the, and here once again we are going to see the channel flow going from left to right. Okay, so this is visualization of the streamwise velocity. You have also access to the vertical velocity and the Z velocity. You can save more snapshots if you want. Here we only save 10 snapshots. So you have access to the snapshot. I think the most important thing for you is to look at the statistics. So for this, I'm just going to go in the Pi4 directory. There is an example folder, and I'm going to go in the channel. Okay, and what I need to do is I just need to copy two things from the simulation, from the that is the statistics, right? So I want the latest one, so after 100,000 time step, and I also need the yp.dat file that corresponds to the mesh in the y direction. Okay, so here once again I'm using the default parameter provided on GitHub, both for the simulation and the post-processing. If you change the input parameter for the simulation, you need to change the input.json. Here you need to input the correct resolution. So if you remember, it's 128, 65, 64, 824, boundary condition do not change, and you need to change the beta parameters. And here this is the yp.dat file that you are going to read. So as I said before, if you change your input parameter when you run the simulation, you need to update this JSON file. And then there's a channel.py simulation. Here you have nothing to change. The only thing you need to change is at which number of time step you are going to read the data. And you will also see that we have some reference data available. If you want to have more information about the reference data, I suggest you have a look at this Software X paper about Xcompact3d, and you have the figure here, figure 4, and the reference for the channel flow are from Moser and Lee and Vreeman, reference 19 and 20. So if you want to have a quick look at what are those references, this is the Lee and Moser GFM from 2015, and the Vreeman and Querten paper from 2014, providing a database for this test case. So those data are available already on in the Pi4 Xcompact3d channel directory. Okay, so this is what we are going to what we are going to look at here. And then you just Python 3 channel.py, and you get this estimate of the Reynolds star 175, which is a little bit lower than 180, but that's okay. The resolution is not the best. And then you have two PNG files, one for the mean velocity profile, the usual plot here, and one for the RMS component U prime, V prime, W prime, with the reference data. And you can see that there is an excellent agreement for the three component U prime, V prime, W prime with the reference data. I mean, it's not perfect, but if you increase the resolution, you will be on top of the two data sets that are provided. So once again, if you want to compare with different reference data, you will have to modify this channel pi file, but this is written in Python. There is nothing complicated, so I'm sure you will be fine. But as you can see, you just git clone Pi4 Xcompact3d, you do a pip install, and then you just need to copy the yp.file and the min.dat file at the end of the simulation. And that's pretty much it. If you change the input of the simulation, you just need to change the JSON file here with the number of mesh node, size of the computational domain, and the beta parameter. So this is how you generate the statistic. The one last thing I want to discuss with you is how do you change and how do you choose the Reynolds number and the stretching. So in order to do that, if you go back to the Xcompact3d directory examples channel flow, well, there is a file called stretching parameter channel.f90. I will go through it. So what you have to do is, first of all, you have the relation between the Reynolds number that is used as an input in Xcompact3d, which is based on the centerline velocity, and the Reynolds tau, which is the Reynolds at the wall based on u tau. You also have the possibility to change the resolution at the wall in wall units. So here, yp means that equal 1. It means that I want my first mesh node to be located at y plus equal 1, okay, and for a resolution of 128. Okay, so if you compile this code, this small file, you will see that the estimated Reynolds tau for 4200 is 182, which is close to what we want, and the beta parameter to have the first mesh node at y plus equal 1 is 0.2527. Your largest mesh in the center of the channel will be 8 in wall unit, okay, and you will have 5 mesh nodes in the viscous sublayer. By comparison, Chebyshev, you will have 10 mesh nodes in viscous sublayer. I would like to add that it's not possible to change the stretching function. You can only change the stretching parameter. So for example, if you want your first mesh node to be located at y plus equal 2, then the stretching parameter will be slightly bigger. Okay, from 0.25 now you go to 0.86. You can also change the resolution. So you want to have, let's say, 256 mesh node in the y direction. You want your first y plus to be equal to 1. So here you will have a beta of 0.87. If you want to change the Reynolds number, so let's say we're going to try with 10,000, you will see that we are getting close to another well-known Reynolds tau that is 390, for which you have lots of data. So you need to do a bit of tuning. Usually for this Reynolds number, we use 10,200, and you will see that you get something very close to the 395. Sorry, the Reynolds tau 395 that is also available in the literature of the database. And for this resolution, you will need a beta parameter of 0.2288 to get your first mesh node at y plus equal 1. That's it for the channel flow. So I've showed you that you can, within a few hours, you can have a nice turbulent channel flow at Reynolds tau 180. I've showed you the main parameters to trigger turbulence and to start collecting the statistics. I showed you how to look at the snapshots and how to produce some statistics using our Python-based post-processing tools called Py for Xcompact3d. It's still under development, but it's very easy to install with pip.